Hi all, this is lecture 1 for Calc 1, Math 201. And calculus is all about looking at the behavior of functions. So the first thing we want to talk about is we want to talk about the behavior of a function as we get close to a specific point. And what I mean by that is we're going to choose a specific x value that we're going to approach from both sides. So if you think about a point on the x-axis, you can approach that value from the left or from the right, and we're going to approach from both. So as we get close, if we're on a function and we get close to a particular x value, I want to know what's the y value approaching. Okay, and so that's what we're looking for here. We're saying, what does the y value approach, or what does the function approach, right? The function represents the y value as the x value gets close to a particular number. So let's take a look at this example. What number does the function f of x equal x squared plus 3 over x approach as x gets close to 1 but not equal to 1, right? Well, why is the but not equal to 1 part in there? Well, you've already done that. You know how to plug function numbers in, right? So if I wanted the value at 1, we would plug in 1 and get a value, right? But that's not what I'm asking here, okay? What I'm asking here is, what do we approach, okay? And so what that means is we want to approach the number 1 from both sides. And I'm going to think about it this way. So that means I'm going to choose numbers on the right to see what's happening with the function and numbers to the left of 1 to figure out what happened. And I want to be super close, right? I don't want to talk about what's happening over at like 2, which would be way over here, right? I want to know what's happening really close to 1 so I can get a really accurate answer. So I'm going to choose 3 numbers on each side, and I'm going to make them really close. So I'm going to make it within a tenth, so 1.1. And actually, let me give that a little room. I'm going to choose within a hundredth, so 1.01. And I'm going to choose within a thousandth, so 1.001. Right? Okay. Make sure, by the way, that your numbers are on as if they were on a number line. So I want to be slightly larger than 1, slightly more larger than 1, slightly more larger than 1. Okay. Okay. And keep in mind that I can get closer and closer to 1 by putting more and more zeros in here, right? Because then I'm adding a smaller decimal value, and so it makes it closer to 1. Now, if I would do the same thing on the other side, I want to go down or less a tenth. So 1 minus a tenth gives you 0.9. So I'm going to put that over here. Minus a hundredth would give you 0.99. And minus a thousandth would give you 0.999. Okay. So now what's going on, and these are x values up top, and I'm going to put function values on the bottom. Okay. Because I know where I want my x to go. I want to approach this value, but I'm going to do it from the right and from the left, okay? And so the question is, if I do the same thing on the bottom, if I plug these numbers into my function and get some values here on the bottom, as I go this way and this way, what do the function values approach? Okay, that's what it means. That's what we're trying to do here. Okay, so let's go ahead and do that. So the next thing that we need to do is we need to find the function values, which means we need to plug these values into our function. And our function is this one. So we're going to plug in the 0.99, 0.99, 0.999 into the x squared plus 3 over x. If you have a graphing calculator, you can use your store function to help you out. And the way that you do that, and I can show this to you more in class, is you hit what you want to plug in, so 0.9, and hit the store button, which is right above your on button, and then choose a letter. So above my math button is A, so I hit the alpha A button. And if you hit enter, then it comes up with 0.9. And now that means 0.9 is stored in your A value. And then I want to put in my function because I'm trying to plug 0.9 into the x squared plus 3 over x. So use good parentheses, and I put in parenthesis a squared, and I know you can't see this, but I'm talking you through, plus 3 parentheses divided by alpha A. And then I hit enter. And what I get here is 4.23 when I plug in 0.9. And so now what I want to do is now I want to change the value stored in A. So instead of 0.9 being there, I'm going to put 0.99, store alpha A, enter. And that puts 0.99 in my A. And then I can go back to that same formula that I used last time. So second entry, so if you put second and enter, that's the entry button. And if you do that twice in a row, your formula will come back up. So A squared plus 3 over A. And hit enter, and this time I get 4.02. And then I can take 0.999 and store that as my A. Second enter, and that will give me 4.002. Okay, so you can kind of see what's happening as we go this way. Where is my value approaching? Okay, and then let's go over here and do the same thing. So now I'm going to store my 1.1. So 1.1 store alpha A. Second enter twice to get 3.83 as my value when I plug in 1.1. Same thing with 1.01, store that in your alpha A, second enter, and I get 3.98. And last but not least, 1.001, store in your alpha A, second enter, and that gives me the 3.99, okay? Okay, now we look for patterns. What's happening? Okay, so on the left-hand side, we're going from 4.23 to 4.02 to 4.002. And so what's happening is my decimal after the 4 is getting smaller and smaller and smaller. So what I'm doing is I'm approaching 4 here. From the right, when I go from 3.83, 3.98, 3.99, again, I'm approaching 4. Now, I said that we've got to approach from both sides. So the only way that I can get an answer here is if these two things match, and they do. So therefore, I'm approaching 4 from both sides. Okay. So my answer here is we approach f of x approaches 4 when x approaches 1. Okay. All right, now let's try another one to see if this can work again. So this time, what number does the function f of x equal x squared plus 3 over x, so same function, approach as x get close to 0 this time, okay, but not equal to 0. Now, why again does that work? Well, back here, you might say, well, if we plugged in 1 squared is 1 plus 3 is 4, divided by 1 gives me 4. So the actual value here, f of 1, is 4. And those two things do match, right? So why would we do this? Well, that doesn't always work, right? If you take this one and you try to take x going to 0, if you plug 0 in here, you're going to divide by 0. You get 3 over 0. That doesn't make any sense, right? It's undefined. And so we don't get an answer. But maybe we can find out more information if we look at where we're approaching. So that's why this is valuable. All right, so let's set up the same thing. We're putting 0 in the middle this time because that's the x value we're approaching. We're going to see what happens to our function. And again, I want 3 numbers super duper close. So larger than 0 are going to be positive numbers. So let's see, that's 0.001, 0.01, and 0.1, right? A tenth, a hundredth, and 1,000 larger. And the other direction, if we go smaller than 0, those are going to be negative numbers. So I'm going to get negative 0.001, negative 0.01, and negative 0.1. And we're plugging that into the same function. So hopefully you've still got that stored in there. And we're going to keep calculating. So I'm going to go start with the positive side, and I'm going to put in 0.1. So 0.1, store alpha A, second enter. And we get 30.1. Next, I'm going 0.01. Same thing, same deal. This time I get 300.01. And last one on this side, store alpha A, my 0.001, second enter, and I get 3,000.01. Take a look at that pattern. What's happening as we go from 30 to 300 to 3,000? If I keep putting zeros between the 0 and the decimal place, what's going to happen to that number? Well, it's going to keep getting bigger and bigger and bigger and bigger and bigger. And what we say there is that it's headed to infinity, right? It's going to continue getting larger infinitely. What happens on the negative side? Well, let's try it out. So this time store negative 0.1. store in your alpha A, plug it in, and I get negative 30.1. Negative 0.01, store that one and go. Gives me negative 300.01. And negative 0.001, store that and plug in, and I get negative 3,000.01. Oh, 0.001. Okay, now what's happening here? Well, I'm still going from 30 to 300 to 3,000, so the number part is getting bigger, but now it's all negative. So this time, as we move in this direction, it's going to infinity, but now they're all negative. So now what happens from both sides? Well, from one side, we're going to negative infinity, and one side, we're going from positive infinity. Are those two things ever going to match up? No. So in this case, when they don't match, what we say is that the limit, or this doesn't exist. Right? There isn't a value, a number, because, right, the question is, what number does the function approach? Well, there isn't a number that it approaches from both sides. So therefore, that number does not exist. Okay, so when we can't get an answer, we say that the answer does not exist. Okay. Now we want to give this a name so that we can stop calling it all these words. And this is called finding a limit. Okay, so finding a limit. And that's what we're going to call it, right? So this process is called finding a limit. So the definition, the limit of a function. Okay, so we're going to get some notation involved in here. All right, so this is what we want. We want the value of a function f of x can be made as close to L as desired. Okay, so as close as we want by taking x as close to A as necessary. Okay, and all of those letters go with this notation. So we would say the limit, and I'll try that. My limit notation tends to deteriorate. So let's see if I can make it pretty at least the first time. There we go. And underneath, we're going to tell it where it's going. So the limit as x goes to, we're going to put in the letter A here because we're going to give it notation. We want it to be generic. Of your function is equal to L, right? So that's your notation for limit. And that means the value of a function f of x can be made as close to L, the value of the limit, as we want by taking x as close to A as necessary, right? So I can keep making my x values as closer and closer and closer and closer to that A value that I want, and I'll get closer and closer to L, right? And what that means up here, you can see, right? I can take my values up top, these right here, closer and closer to my A value, which is 1, and that will get me closer and closer to the value that I say is the L, which is 4 in this case, right? So 4 is the answer where the function approaches. So let's take a quick peek. So that means for our example up above, that meant that the limit as x went to 1, right? In our first case, the A value was 1, and the function was x squared plus 3 over x. And our answer, the number that the function approached, was 4. For the second one, we had the limit as x goes to 0, this time, of the same function, x squared plus 3 over x. And this one, we just say it does not exist. We use D and E to represent it there. Okay. Okay, so it's possible that our limit exists and it's possible that our limit does not exist. We saw one of each of those types of examples. But notice that in each of these cases up here, regardless of whether I had, whether they matched, I could figure out where each side was approaching. Okay, it might be infinity or negative infinity, but I could tell where the numbers are going, right? And so we call those one-sided limits, right? When we were doing a limit in general, it's from both sides, but you can talk about one side or the other separately. And we call those one-sided limits. So there's a left-handed limit and a right-handed limit. So if you're thinking about looking at a graph, the left side is where the smaller numbers and the negative numbers are. And so notice that in my notation here, there's a little negative sign right there. So that negative means left-handed side, right? And so from our examples up above, from the first one, we would say that our limit as x went to 1 from the left of x squared plus 3 over x was 4. Right? From the left, it was 4. And in our second example, the limit as x went to 0 from the left of x squared plus 3 over x, that one was negative infinity. Okay, so your answer doesn't have to be a number. It could be positive or negative infinity as well. And on the right-hand side of the graph is the positive numbers, and that's why you'll see this little positive symbol right here. Okay, and that represents a right-handed limit. And so for our examples, we have our limit as x goes to 1 from the right of the x squared plus 3 over x. That was also 4. And our limit as x went to 0 from the right of x squared plus 3 over x in that second example. Now on the right-hand side, we were approaching positive infinity. Okay. And what we know here is that your left-handed limits or your right-handed limits will always exist. Okay. The only reason the one up above didn't exist is because the left and the right didn't match. Okay. And so that's the next statement that we want to make. Okay. We want to say that if the limit as x goes to a of f of x equals L exists, if and only if, and we'll talk about that in 1 second, the limit from the right and the limit from the left are also L. Okay. If and only if means that the statement goes both directions. So if we have the limit as x goes to a of f of x equals L, that's the same in both directions as if this is true. The limit as x goes to a from the right is equal to the limit as x goes to a from the left. And those both have to be L. And what that means is that if you know that the limit from both sides is L, that tells you what the right and the left is. Right? And if you know that the right and the left are equal, then you know what the whole limit is. Okay, so that's what the if and only if means. Okay, so now we just want to go through a couple quick examples of what we mean. All right, here we go. So we're going to use our chart, same way that we did before. We're going to set up our A value, which is this one here. The value that we're approaching, so the 3 goes in the middle. And again, I want you using 3 values. So I want to add 1,000th, 100th, and a 10th. And I want to subtract. So if I subtract it, it's going to be 2.99, 2.9, oh, add another 9, and 2.9. So this is my x, and this is my f of x. And this time, I'm plugging into this function. Okay. So use your calculator and go ahead and get that. So again, you're going to store that one of those values. So if you start with a 3.1, store it in your alpha A. And we're going from there, right? So we get, you're plugging that into your function here. You've got 2 alpha A squared minus 18, use your parentheses well here, over A minus 3. And when I plug that in, I'm going to get 12.2. And just so I can speed up the video a bit, go ahead and pause it, see if you can plug them all in and see what you get. You get 12.02. and 12.002 here when you plug in. On the other side, if you do the same thing, plug in these same three values, you get 11.8, 11.98, and 11.998. Okay. Okay, so now what we want to do is we want to look at our limits. So now we're going to use all of our notation. We're going to practice here. So from the right-hand side, that means this side, and we're going towards the 3. You're going from 12.2, 12.02, 12.002. And so I'm approaching 12 from that side, right? So that tells you that the limit as x goes to 3 from the right of your function, 2x squared minus 18 over x minus 3, is 12. And on the left-hand side over here, we're going from 11.8 to 11.998. So the limit as x goes to 3 from the left of 2x squared minus 18 over x minus 3 is also 12. Okay. And now based on this information, because those two values are the same, my one-sided limits match, that tells me that the limit as x goes to 3 from both sides, so I don't use a plus or a minus now, 2x squared minus 18 over x minus 3 is going to be 12. Okay, and then we're going to do that same thing for the next two. So for number 2, we're going to put a negative 2 in the middle. Okay, now closer, remember zero's over here, right? If we're thinking about this being on a number line. So I need closer to 0 would be negative 1.999. Negative 1.99, they kind of switch sides. Negative 1.9. And then over here, you got negative 2.001, negative 2.01, and negative 2.1. And we're plugging that into our function. And again, go ahead and pause the video, see if you can plug those into your calculator. But what you should get, as I've done this ahead of time, you should get negative 0.9, negative 0.99, negative 0.999. Over here on the right, you're getting negative 1.1, negative 1.01, negative 1.001. Okay, so what's happening? On the right-hand side, as we get closer to negative 2, we're going from negative 0.9 to negative 0.999. So we're approaching negative 1. So we'll have the limit as x goes to negative 2 from the right of our function, and I'm going to just put f of x in there for now, is going to be negative 1. And from the left-hand side, so that's our limit as x goes to negative 2 from the left. As we go this way, you're getting closer and closer to negative 1. And so together, because they match, we get the limit as x goes to negative 2 of your function as negative 1. Okay. Uh-oh. I'm missing a value here. We're going to go with 4. So number 3, we're going to put a little 4 here. So we're going to take the limit as x approaches 4, and we've got x squared plus 2 over x. So we're going to have a 4 in the middle. You're checking 4.001, 4.01, and 4.1. 3.999 on the left, 3.99, and 3.9. And you're plugging into that function. All right, now I'm a little behind on this one, so let's see if I can calculate them real quick. I've got, so for 4.1, I've got 4.59. I've got 4.51. And I've got 4.501. On the right-hand side, if I use the 3.9, I've got 4.41. I've got 4.491. and I've got 4.4991. So what's happening here is we go this way, I'm getting closer and closer to 4.5. And when I go from this direction, I'm getting closer and closer to 4.5. Okay, so notation-wise, that tells us that the limit as x goes to 4 from the right of x squared plus 2 over x is 4.5. The limit as x goes to 4 from the left of x squared plus 2 over x is also 4.5. And that tells me that because they match, the limit as x goes to 4 from both sides, so nothing after it, x squared plus 2 over x is also 4.5. Okay, so we want to be able to use a little chart to calculate. Okay, now the other thing that we want to be able to do is we want to be able to look at a graph and identify what the limit is. So the next couple, we're going to use a graph to find the specified limit. All right, so how are we going to do this? Grab your graphing calculator. I'm going to go to Wolfram Alpha. If you don't have a graphing calculator, what you want to do is go to wolframalpha.com. And then in this little orange box at the top, you're going to ask it to plot and then whatever function you want. Okay, so I've got, let's see, use my parentheses well. So x squared, oh, nope, cubed, plus 2x plus 1 divided by x plus 2. And hit go. And once you do, it's going to give you two different graphs. One zoomed in, right? Notice this is from -3 to 7.3. And this one's a little bit more zoomed out because it goes from about -30 to +30. But we want to know what happens when the limit approaches -1, right? It says the x goes to -1 of this function. So that means what I'm going to do is I want to go to where -1 is. So -1 is right here-ish. If I can get it to pick the spot. Let's see here. Nope, it won't let me do it. There we go. That's close enough. Okay, so -2 is 4 notches out. So that means that -1 is 2 notches out. And we're going to find the point on the graph, so on the blue curve. And we want to know at -1 on the curve, what's the where is the y values approaching? And they're approaching this value on the y-axis, which is that first tick mark. And let's see, each tick mark looks like it's 2, so that's going to be -2. So we're going to have -2 here. Okay. And we're going to do the same thing for each of these. So x squared minus 2x minus 3. Sometimes typing it is what takes the longest. Again, if you've got a graphing calculator that you like, that's fine too. All right, we've got x squared minus 5x plus 6 on the bottom. And hit go. And there's our graph. And we're approaching this when the limit is as x goes to 3. So we're going to zoom in here to this spot right here. And that looks like it's approaching 4 from both sides. So let's jot that one down. This one appears to be 4. All right, the next one, number 3, where it's the same graph, so I can stay on this graph, but the limit value changed. So now we're going to x equals 2. Uh-oh, take a look at what happens at x equals 2. If I approach from the right, if I'm following the blue line from the edge towards that gray vertical line at 2, notice that the blue values go up along that line. And on the left, those go down. So when it goes up, that means your values are going to positive infinity. On the left, when it goes down, it means they're going to negative infinity. And so what happens with this one is you get the limit as x goes to 2 from the right of this function was positive infinity. And I'm writing the plus there for emphasis, so you don't need it. And the limit as x goes to 2 from the left was negative infinity, right? And we said when those two things don't match, then the limit as x goes to 2 of your function does not exist. So our answer here is going to be does not exist. Okay. So that's what the graph looks like when it does not exist. It looks just like that, right? There's essentially an asymptote there often. All right, let's grab the next one. So this one is going to be x cubed minus 64 divided by x squared. Actually, I'm going to do this, and then I'm going to change it because it'll save me a step. X squared minus x minus 12. And we can go on that one. All right, here it is. And we're looking when x equals 4, which is this value out here. And it looks like that is something that's close to 7-ish, right? So we're going to say approximately 7, right? This is all approximate because we're just kind of looking at the graph, right? And then last one, we've got this square root going on here. And so let's graph that one as well. You're going to plot square root and then x plus 12 minus 3. Close your parentheses, then divide by x plus 3. And you can see that this one looks a little bit different. And at negative 3, which is over here, we get something that looks like, oh, I don't know, 0.17 maybe? So approximately 0.17. Okay, so we can use the graph there as well. Okay, so from here, we're going to head over to the guided practice and let you practice a few of these, and then we'll go from there.